Welcome back to Baremetalcyber. Thanks for joining me. Today we're tackling a topic that's reshaping the foundation of digital security: quantum computing and its impact on cryptography. As quantum computing advancements push the boundaries of computational power, the encryption methods we've trusted for decades are facing unprecedented threats. In this episode, we'll explore the vulnerabilities exposed by quantum computing, the urgent need for post-quantum cryptography, and the global efforts to create quantum-resistant standards. We'll also explore how this technological revolution impacts industries, governments, and everyday users, while examining what's being done to ensure a secure future in the quantum era. Let's dive in. The advent of quantum computing marks a transformative moment in the evolution of technology, with profound implications for cryptography and digital security. Traditional cryptographic methods, which underpin the confidentiality and integrity of modern communications, are increasingly vulnerable to the promise of extraordinary computational power from quantum systems. Algorithms like RSA and elliptic curve cryptography, once considered unbreakable by classical means, were at the risk of becoming obsolete as quantum breakthroughs accelerate. The quantum computing threat to classical cryptography. Quantum computing represents a revolutionary shift in processing information, operating on principles that diverge significantly from traditional computing. In classical systems, data is represented by strictly 0 or 1 bits. Quantum systems, however, use quantum bits, or qubits, which can simultaneously exist in a superposition of states representing both 0 and 1. This means quantum computers can perform multiple calculations simultaneously, vastly increasing their power for specific problems. Another quantum property, entanglement, allows qubits to become interconnected, such that the state of one directly influences the state of another, regardless of physical distance. These properties enable quantum computers to tackle problems that would take classical computers millions of years to solve. Research organizations like IBM and Google are leading advancements in quantum computing, with notable achievements such as Google's claim of quantum supremacy, where its quantum processor solved a problem in seconds that would take a supercomputer thousands of years. One of the biggest threats quantum computing poses is to the cryptographic systems that secure our digital world. Many of these systems rely on the difficulty of mathematical problems such as factorization. Factorization involves breaking a large number into prime components, numbers that can only be divided by 1 in themselves. For instance, the number 15 factors into 3 and 5. While this is easy for small numbers, it becomes computationally unfeasible for large numbers, which is the basis of RSA encryption. RSA relies on the fact that classical computers would need an impractical amount of time to factorize the enormous numbers it uses as keys. However, Shor's quantum algorithm, can perform this factorization exponentially faster, rendering RSA encryption vulnerable. Similarly, elliptic curve cryptography, or ECC, built on different mathematical principles, would also be compromised. On the other hand, symmetric key systems like AES are more resistant because they don't rely on factorization, though they would still need longer keys to withstand quantum attacks. The potential consequences of these vulnerabilities are far-reaching and deeply concerning. Cryptography secures everything from bank transactions to government communications. If quantum computers break widely used encryption schemes, sensitive data stored today, such as financial records, medical histories, or classified government information, could be decrypted. This is known as harvest now, decrypt later, where adversaries collect encrypted data knowing they can crack it once they have quantum capabilities. Blockchain technologies, which rely on cryptographic signatures for security, would also be at risk. Cryptocurrencies like Bitcoin could lose their integrity, as quantum computers could forge digital signatures or alter transaction records. Such vulnerabilities extend beyond individual systems, threatening the global financial sector, military operations, and even international security infrastructure. The broader implications of quantum threats to cryptography cannot be overstated. As nations race to develop quantum technology, those with the most advanced capabilities could gain a disproportionate advantage in cybersecurity and intelligence. This could lead to geopolitical imbalances where countries with quantum dominance could potentially undermine the security of others. Additionally, the interconnected nature of today's digital systems means a vulnerability in one area can ripple across industries, amplifying the impact of quantum-enabled attacks. Acting against these risks will require unprecedented collaboration between governments, industries, and researchers to develop quantum-resistant solutions and implement them before adversaries exploit these weaknesses. Given the rapid pace of advancements in quantum computing, the time to act is now. While fully operational quantum computers may still be a decade away, preparing for their impact requires immediate investment in post-quantum cryptographic solutions. These new algorithms resist quantum attacks while maintaining compatibility with existing systems. However, transitioning to quantum-resistant encryption is a complex process involving technological upgrades, training, policy changes, and widespread adoption. The cybersecurity community must lead this effort, combining education, innovation, and collaboration to safeguard the digital ecosystem. By taking these steps, we can ensure that our security frameworks are prepared for the transformative challenges of quantum computing. An overview of post-quantum cryptography, PQC. Post-quantum cryptography, PQC, is an emerging field aimed at addressing the vulnerabilities of traditional cryptography in a world with quantum computers. Its goal is to develop cryptographic methods that resist attacks from quantum algorithms, which can solve certain problems far faster than classical computers. PQC methods differ from traditional cryptography because they avoid relying on mathematical problems like factorization or elliptic curve calculations, as we discussed before. PQC is built on computationally challenging issues, even for quantum systems. By adopting these new methods, organizations can ensure their digital security remains robust now and when quantum computing becomes mainstream. Several PQC algorithms are being explored, each based on unique mathematical principles that make them resistant to quantum attacks. For example, lattice-based cryptography uses structures that resemble grids in high-dimensional spaces. Solving problems within these lattices, like finding the shortest vector on a high-dimensional grid, is incredibly complex and resistant to quantum computation. Code-based cryptography, such as the classic McLeese, relies on error-correcting codes to secure data. Code-based cryptography makes it extremely difficult for an attacker to reverse engineer the encryption, even with a quantum computer. Multivariate polynomial cryptography uses systems of complex polynomial equations. Solving such systems is computationally expensive even for quantum processors. Lastly, hash-based signature schemes, like Sphinx Plus, depends on the security of hash functions, algorithms that transform data into fixed-size outputs in a nearly impossible reverse way. Hash functions are one of the few cryptographic tools believed to remain secure against quantum attacks. Key properties of PQC make it suitable for use in various real-world applications. These algorithms must be quantum-resistant, meaning they're designed to secure even the advanced capabilities of quantum computers. At the same time, they must perform well on today's classical computers, since widespread adoption will occur long before quantum systems are common. Compatibility with existing infrastructure is crucial, allowing PQC to work alongside legacy systems without requiring a complete overhaul of digital environments. Additionally, PQC must be versatile enough to handle diverse scenarios, such as securing IoT devices with limited computational power or protecting blockchain systems which rely heavily on cryptographic integrity. The global push for PQC involves collaboration across industries, governments, and academia. One major effort is the NIST PQS standardization project, which identifies and evaluates quantum-resistant algorithms to establish new standards. I'll be discussing this more in detail in a few moments, but it has been a critical driver of PQC development. Beyond NIST, tech companies, research institutions, and international organizations collaborate to accelerate progress. Open-source contributions also play a vital role in fostering transparency and encouraging innovation from the global research community. These efforts are essential because quantum-resistant security is a challenge that transcends borders, requiring collective solutions to protect interconnected digital systems. Understanding PQC and its significance is essential as quantum computing continues to advance. Unlike the encryption methods we use today, PQC ensures that digital security can endure even when faced with the extraordinary capabilities of quantum machines. The transition to PQC is not just a technological change. It's a proactive step to safeguard sensitive information, critical infrastructure, and global cybersecurity. Through sustained collaboration and investment, the cybersecurity community can ensure a future where encryption remains a reliable foundation for trust in the digital age. Emerging cryptographic standards. The emergence of quantum computing has necessitated the creation of new cryptographic standards to ensure the continued security of digital systems. The NIST post-quantum cryptography PQC standardization process is central to this effort. This initiative identifies and standardizes quantum-resistant algorithms to replace or augment existing cryptographic methods. The process is structured into multiple phases, starting with an open call for algorithms, followed by rigorous evaluation rounds. These evaluations assess the algorithms for security, performance, and adaptability, ensuring they resist quantum and classical attacks, operate efficiently on current hardware, and can integrate into existing systems. Global experts, including researchers and industry leaders, participate in this process, making it a collaborative and transparent effort. Among the finalists identified by NIST, several algorithms stand out for their specific use cases. Crystal's S1E2 is a key encapsulation mechanism designed to securely exchange cryptographic keys, a crucial component in encrypted communication. It is valued for its efficiency and small key sizes, making it suitable for resource-constrained devices. For digital signatures, algorithms like Crystal S Dilithium, Falcon, and Sphinx Plus offer robust options. Digital signatures verify the authenticity of data and communications, ensuring they haven't been tampered with. Each algorithm has unique strengths. Crystal's dilithium is highly efficient. Falcon offers compact signatures, and Sphinx Plus provides strong security even if its key sizes are larger. These algorithms address different practical scenarios, from securing IoT devices to protecting government communications, making them versatile tools for post-quantum cryptography. Preparing industries and governments for the transition to these new standards is a complex but essential task. Major technology companies are already testing and implementing quantum-resistant algorithms in their systems. Governments also take proactive steps by developing readiness programs and issuing directives to encourage early adoption. International standards organizations like ISO and IEEE are critical in aligning global efforts, ensuring consistency and interoperability across borders. Outreach and education are also equally important, as stakeholders from diverse sectors must understand the implications of quantum threats and the steps needed to address them. These initiatives aim to create a smooth transition to post-quantum security, minimizing disruptions and ensuring widespread adoption. Despite these efforts, several hurdles remain in standardization and implementation. One major challenge is balancing security with usability. Quantum-resistant algorithms often require large keys or more computational resources. These impact system performance. Ensuring backwards compatibility with existing systems is another critical issue, as organizations cannot overhaul their infrastructure overnight. Cost is also a significant factor, as upgrading cryptographic systems at scale requires substantial investment. Additionally, there may be pushback and skepticism from industries reluctant to adopt new technologies or uncertain about the timelines for quantum threats. Addressing these concerns will require clear communication, robust testing, and incremental implementation strategies. The journey to establishing and adopting emerging cryptographic standards is urgent and complex. Quantum computing presents a direct challenge to the cryptographic methods that secure today's digital world, and the NIST standardization process is a vital step in mitigating that risk. By identifying robust, efficient, and adaptable algorithms, NIST and its global collaborators are laying the foundation for a secure post-quantum future. However, the success of this effort will depend on widespread collaboration, education, and investment to overcome the technical, economic, and organizational challenges ahead. With continued focus and preparation, industries and governments can ensure a seamless transition to quantum-resilient security. Challenges in post-quantum deployment. Deploying post-quantum cryptography introduces numerous challenges, particularly regarding technical integration. One major concern is the performance overhead associated with quantum-resistant algorithms. These algorithms often require larger key sizes and more computational resources, which can increase latency, the time it takes to process data, and bandwidth usage. This is particularly problematic for devices with limited computing power, such as IoT devices or legacy systems that can't handle the added resource demands. Compatibility with these older systems presents another challenge. As organizations often cannot afford to replace or upgrade all infrastructure at once, hybrid solutions, which combine classical and quantum-safe cryptography during the transition period, further complicate matters. These hybrid approaches may inadvertently introduce vulnerabilities if the integration is not carefully managed and tested against emerging attack vectors unique to the quantum era. Economic and operational barriers also pose significant hurdles to PQC deployment. Upgrading cryptographic infrastructure requires substantial investment, including new hardware, software, and ongoing maintenance. For many organizations, allocating these resources is difficult, particularly in industries with tight budgets or competing priorities. Additionally, transitioning to PQC necessitates retraining personnel to understand and implement the new systems. This retraining introduces skill gaps that can slow adoption and increase the risk of errors. The migration process carries disruption risks, such as temporary system outages or unexpected compatibility issues. Uneven adoption across sectors and regions further complicate matters. as a lack of global alignment creates vulnerabilities in interconnected systems that rely on consistent security standards. Transition phase to PQC also introduces unique security risks. Poorly implemented or incomplete quantum-safe solutions can undermine the protections they are intended to provide. For example, using hybrid cryptographic environments where classical and quantum-resistant methods coexist may create exploitable weaknesses if attackers can target the weaker classical components. Adversaries with evolving quantum capabilities also represent a moving target, as their ability to exploit cryptographic vulnerabilities will improve over time. Continuous monitoring and iterative improvements in cryptographic systems are essential to address these risks. Organizations must adopt a proactive approach, regularly updating their security measures to anticipate and mitigate new threats. Coordination across borders is another critical challenge in post-quantum deployment. Cryptographic policies and regulations vary widely between countries, creating inconsistencies that can hinder the global adoption of quantum-resistant standards. Collaborative frameworks are essential to align efforts and meet shared security goals. Intellectual property and open-source considerations add further complexity, as the development and deployment of PQC solutions also involves contributions from multiple stakeholders. Balancing transparency in the development process with national security interests is a delicate task, as too much openness may expose vulnerabilities, while excessive secrecy can limit collaboration and innovation. Achieving this balance requires international cooperation and trust among governments, industries, and research institutions. Successfully overcoming these challenges is vital to ensuring the secure deployment of PQC across industries and nations. With proper planning and collaboration, the technical, economic, security, and geopolitical hurdles are significant but not insurmountable. Governments and organizations must prioritize investments in quantum-resistant infrastructure, provide education and training for stakeholders, and foster global partnerships to create unified standards and frameworks. The future of cryptography in a quantum world. The future of cryptography in a quantum world extends beyond the current focus on PQC. As quantum computing continues evolving, researchers are exploring novel cryptographic techniques beyond quantum-resistant algorithms. One such avenue is quantum cryptography, particularly quantum key distribution, QKD, which leverages the principles of quantum mechanics to provide theoretically unbreakable encryption. Unlike classical cryptography, QKD detects any eavesdropping attempts in real time, adding a layer of security that traditional methods cannot match. Additionally, artificial intelligence, or AI, is being studied as a tool for creating adaptive cryptographic systems capable of responding dynamically to emerging threats. AI could identify potential vulnerabilities in cryptographic systems and develop countermeasures faster than human analysts. However, as these technologies evolve, so do attack surfaces, requiring proactive research to anticipate and mitigate new risks posed by increasingly sophisticated adversaries. Global cooperation will play a critical role in shaping the quantum cryptographic landscape. International agreements on quantum security standards are essential to ensure interoperability and shared protection across borders. Public-private partnerships can drive research and development, pooling resources and expertise from governments, industry leaders, and academia to accelerate innovation. Cross-border intelligence sharing and coordinated threat assessments will be crucial for identifying and addressing vulnerabilities in real time, as national boundaries do not confine quantum threats. Ethical and privacy concerns must also be addressed as new technologies emerge. Ensuring quantum cryptography respects individual privacy rights and avoids misuse is vital for maintaining public trust and upholding the ethical standards in global security practices. Quantum's influence extends to securing emerging technologies, which are increasingly integral to modern infrastructure. Quantum-safe solutions are essential for the IoT and edge computing, where devices often operate with limited resources and particularly vulnerable to cyber attacks. Blockchain and distributed ledger technologies also benefit from quantum-resistant measures, as their reliance on cryptographic integrity makes them prime targets for quantum-enabled adversaries. AI and machine learning systems, which play a growing role in decision-making processes, must also be secured against quantum threats to protect sensitive data sets and ensure algorithmic integrity. Finally, critical infrastructure, including energy grids, supply chains, and communication networks, must be fortified with quantum-resilient measures to prevent catastrophic disruptions in the face of future cyber attacks. Building a quantum-resilient security framework requires strategic planning and investment at multiple levels. Education and workforce development are essential to equip future cybersecurity professionals with the knowledge and skills needed to implement and manage quantum-safe systems. Strategies for scaling PQC adoption must address the technical and logistical challenges of deploying new algorithms across industries, ensuring that solutions are practical and accessible. Realistic timelines for quantum breakthroughs must be estimated to guide global efforts, balancing urgency with feasibility. Above all, resilience must be a cornerstone of the security framework, focusing on adaptability and preparedness in a rapidly changing technological landscape. Organizations must prioritize iterative improvements and maintain flexibility to address evolving quantum threats. The quantum era presents both challenges and opportunities for cryptography. By embracing innovation, fostering international collaboration, and integrating quantum-resistant measures into emerging technologies, the cybersecurity community can safeguard digital systems against unprecedented computational power. In conclusion, the rise of quantum computing represents both a challenge and an opportunity for the cybersecurity community. While its unprecedented computational power threatens to undermine traditional cryptographic systems, it also drives innovation in developing quantum-resistant solutions and exploring novel security measures. The global effort to establish post-quantum cryptographic standards and advancements in quantum cryptography and AI provide a strong foundation for building a resilient digital future. By addressing technical, economic, and operational challenges and fostering international cooperation, the cybersecurity community can ensure the continued protection of critical systems and sensitive data in the face of quantum advancements. With careful planning and a forward-thinking approach, the transition to a quantum-secure world can mitigate risks and pave way for new opportunities in digital innovation and security. Thanks for tuning into this episode of Baremetalcyber. If you enjoyed the podcast, please subscribe and share it. You can also follow me on LinkedIn for more cybersecurity insights and updates at jason-edwards.me. Be sure to join the tens of thousands already subscribed to my newsletters, where I share exclusive content on cybersecurity, leadership, and education. And don't forget to check out my author page at cyberauthor.me, where you can explore my books on cybersecurity and more. I truly appreciate every listen, follow, and share. Until next time, stay safe and remember, knowledge is power.